So hi everyone, welcome back to the CSP seminar. So this is the first seminar after spring break, and it's our great pleasure to have Christos from University of British Columbia to give us a talk on his recent work on finding and leveraging structure in large models in balance and trouble. He is an assistant professor in Department of Electrical and Computer Engineering at University of British Columbia. Previously, he was an assistant professor at University of California, Santa Barbara, and a postdoc researcher at MIT. And he received his master's and PhD in electrical engineering, both from Caltech. And his research interest is mainly focused on machine learning, high-dimensional signal processing, and statistics, and optimization. So let's welcome Christos for his talk.
Thank you very much, Singh. Thanks again for the invitation. I would have very much liked to be there in person as well, so I apologize for not being able to make it last minute for the trip. Nevertheless, I hope that I'm glad I still am given the chance to present this online. So thanks for your time in advance. So I understand that some of you in the audience are going to be very familiar with many of the things that I will be discussing, but I've kept things I'm hoping appropriate for a more general audience. Nevertheless, since it's a little bit difficult for me to really see you or see the chat, I would appreciate if you can just stop me and ask questions as I go on. Okay, so indeed, what I want to talk about is some of the work that we've been doing recently in the group on finding and leveraging structure in large models, and specifically I'm going to be talking about how the structure possibly changes and how we can leverage the structure when data are imbalanced. But let me start by explaining and giving a little bit of context of what I mean by large models. So by large models in this talk, I'm going to mean models that are over-parameterized, and this is typical in modern deep learning. We have neural networks that have a number of parameters that is much larger than the number of examples, and what this means is that essentially you can drive the training accuracy to 100% during training, and while you're doing that, you also empirically achieve very good generalization. Okay, so this trend for larger and larger networks is something that has been ongoing for several years now and continues to be the trend. This figure here from a paper in 2019 is by now rather outdated, but it still does show the trend. So you see here that some of the best performing neural networks, and again, best performing in the sense of top one accuracy, generalization accuracy, are such that the number of parameters is much larger than the size of the training data set. And so really I would say that the holy grail question in understanding such large models or over-parameterized neural networks is why do they generalize well? And there's been arguably lots of interest and lots of work in the past few years in trying to address this question. There's different approaches, and what I'm going to discuss today is one potential pathway towards answering or towards getting a better understanding of this question. And so a conceivable step in this direction that we're going to follow in this talk is to try to understand whether there are structural properties of the solutions that are being learned by these large models. And what I mean by structural properties, I will be making this more and more specific as I go further in the talk, but what we'll see is that I'll be talking about the geometry of the learned weights. So is there something that we can say about this geometry? Now, before I specify further what I mean by geometry, let me make the setting clear. So I will be talking about K-class classification. So nothing new here. This is a standard classification setting where we're given n training data that consist of pairs xi, yi. Xi are the raw features. These are p-dimensional vectors. Think of them as vectorized versions of images that you want to classify in K classes. And the way that you will do classification is by learning a model, f sub theta. So this model is a mapping from the space of raw images from the raw embeddings, R to the p to a k-dimensional vector. And the way that you predict a label is by looking at this k-dimensional vector, the output of the model, picking the maximum entry and the corresponding argmax. This is what you call the class that you predict membership of the corresponding example. Okay. Now, the way that neural networks build that model is as follows. Again, these are very basics. I'm just setting up the language. So you take examples that are these p-dimensional vectors, and essentially you learn an embedding, which is a map from Rp to Rd. Okay, so there's some hidden dimension. This is the dimension of the last layer of the classifier. And what you learn is you learn how to map an example xi to an embedding hi. And there's one embedding for each example. And once you have these embeddings, essentially what you do on top of that is you do linear classification. So because you have k classes, you learn k classifier vectors, which you can think of them as a matrix W of classifiers. So this is a D times K matrix where I have K classifiers, one for each class. Each one is a D-dimensional vector. And the overall model is given as the inner product. That's why I said linear classification of W, of this matrix W with the corresponding embeddings. So this is the output of the model. And then you look at the logits, and there's K logits, you pick up the maximum, and this is your predicted label. Now, the whole point of training with neural networks that makes it different than linear training is that you learn the embedding and the classifier jointly. And in a classification setting, typically this is done by minimizing a cross-entropy loss, which you see here, and essentially here the minimization is over the classifier weights and over the embeddings. Now the embeddings are parameterized by theta, where theta is the weights of the neural network. Okay, so these embeddings are parameterized by the specific architecture of the neural network, and the optimization is joined over theta and W. All right, good. So what we're going to do in this talk is we're going to focus at the last part of the neural network. So we're going to focus at the embeddings and the classifiers. So we're going to view the rest of the neural network as a black box, essentially. And the question that I want to ask is whether there is something that we can say about the geometry of these learned embeddings and classifiers when this large overparameterized model is being trained with some first order method, say SGD, and it's being trained until zero cross-entropy loss. Okay, of course, you can't really make your cross-entropy loss zero because this is a loss that asymptotes to zero, but you continue training even beyond the regime where you have achieved perfect training accuracy, and you still drive the error to zero, the loss to zero. And what I mean by geometry, well, I'm asking for something very specific here. Is there something that we can say about the angles and the norms of these d-dimensional vectors? And let me clarify again that what we have here is we have k classifier vectors, and we have n, where n is the number of data points, embedding vectors. And what we want to understand is whether there is something that we can say about the norms and angles of these vectors that are vectors that live in the dimension. Now, of course, this question, I suppose, is rather ambitious. I think you would agree with me, because the answer could depend on many things. It could depend on the very specifics of the architecture. It could depend on the specifics of the data set. It could depend on the distribution of the data set. It could even depend on the specific algorithm that I'm using to do the optimization. And so it's not, I think it's clear to everyone that is not a priori obvious why there should be even an answer to this question. Now, what happened, I guess, around 2.5 years now back, is that Papian, Han, and Donoho submitted this nice empirical work where essentially they did a lot of experiments, and through experiments they postulated an answer to this question. Okay, so here is how the answer, their postulation looks like. So under the setting where all the classes have the same number of examples, the authors claim that this geometry that I mentioned is fully characterized by essentially just two properties. The first property is called the neural collapse property, and the second property is called the ETF property, and ETF here stands for equiangular tight frame. So what I want to do is that in the next couple of slides is I want to introduce these two properties, or remind these two properties to those who are already familiar with them. And so let me start with the neural collapse property. So the neural collapse property says what the name suggests. So embeddings of examples belonging to the same class C collapse to their class mean embeddings. Okay, and there is some formula for it. Let me just explain this in picture. So what this property says is that if you were to look at the examples in the original p-dimensional space, and let's say that we have a 4-class classification setting where I'm trying to separate stars from squares and circles and triangles, then that's possibly how my examples would look in the p-dimensional space. And for each class, there is a corresponding mean vector that I can compute. And naturally, I might expect that the examples are around this mean vector. What this property says is that if I am to look at the same picture, not in the p-dimensional space, but in the space of the embeddings after training has happened, then the picture would look like that. So, so the embedding that is being learned for each one of the examples of each of the class collapses to the corresponding class. So this is the neural collapse property, which is interesting. But what is even more interesting to me is that the postulation made by the author actually tells you something about the specific geometry of these mean embeddings. And this is the ETF property. So what the ETF property says is that these mean embeddings, which are d-dimensional vectors, those are k d-dimensional vectors, they lie in a low dimensional space of dimension k minus 1. Remember that k here is the number of classes. These mean embeddings, they all have the same norm. So this is the picture that you see here again for the example where I have k, where I have 4 classes. So these are embeddings that live in R3, and there's 4 of them. They're all on the same sphere. And on top of that, they are all maximally separated. Okay, so the angles between any 2 of the embeddings is the same. Its cosine is minus 1 over k minus 1. And this is the maximal separation that you can get. And on top of that, the last property is that the classifiers align with the embeddings. Okay, so the picture that you get is as follows. The classifiers and the embeddings, they all live in the same ball. They're aligned and they're maximally separated with each other. Now, the way that you can write this algebraically is by looking at the gram matrix of the embeddings or the gram matrix of the classifiers and say that it converges to this centered version of identity. And but again, by convergence here, what I mean is that it converges as training evolves. So let me show you that. So do these properties again, these are just conjectures, right? Do these properties hold? So here's an experiment that tries to verify whether the neural collapse property holds. So these are replicated experiments from the original paper. So what we did here is we're training ResNet 18 on CIFAR 10 and MNIST, and we're casting some measure of neural collapse, which looks at the differences of the embeddings of each class to the corresponding class mean, and tracks this metric as a function of the epochs. And so what you see here is that as training evolves, this metric converges to 0, which is what neural collapse would predict. And so what you see here is you also see this dashed line, which indicates this indicates the epoch at which I achieve 100% training accuracy. And this is what I was mentioning in the beginning, that this is a setting where training progresses even beyond that threshold. And so the observation here is that both for CIFAR and MNIST, this metric goes down as predicted by the neural collapse property. Now, what about the geometry? I can do the same experiment where now instead of measuring something that corresponds to neural collapse, I'm measuring the distance of the gram matrix of classifiers to the theoretical value. Again, there's no really theory here. It's more of a conjecture. So I'm measuring how far this gram matrix is from the centered version of the identity matrix. And again, I can see this matrix going down as training progresses. The same is true for the embeddings. Although notice that for the embeddings, the convergence is not that fast, and the convergence level is not that low as for classifiers, but still you see that trend that, excuse me, as training progresses, the metric does go down. Okay, so this characterization that was made in the original paper is I think you would agree with me that it's rather simple. To me, it was rather striking in the beginning that such a simple characterization can kind of capture a behavior that is happening in some sense in a cross-situational invariant fashion across architectures and datasets. So I showed you that this is something that holds for CIFAR 10, for MNIST, for ESNet 18. But in the original paper, they actually saw experiments over 7 datasets and 3 types of neural networks. So this appears to be pretty consistent behavior. And really the only restriction in the original experiments and in this conjecture is that the number of classes for each, the number of examples for each class is the same. So we have a situation where we have an entirely symmetric and balanced data set. And so the question that I want to ask and discuss in this talk is, what if data are imbalanced? Okay. Now, why am I interested in imbalanced data? First of all, imbalances are more frequent than not. So if we're trying to understand what is that neural networks learn and what is that they do, then I think it's a good idea to try to understand what is that they do in settings that we encounter in practice, and imbalances are out there. Beyond that, I think there is a more philosophical reason tied to the specific quest of understanding structure and understanding geometry. To me, this original discovery by Papian, Han, and Donoho is a demonstration that it is possible to characterize such structural properties. And so what we wanted to see here is how robust is this investigation, right? So is it only possible to characterize such structure only when things are very symmetric, or is it possible to have such a simple, potentially different, but still simple characterization even when data symmetry breaks? And this is something that potentially we can look by looking at imbalanced data. Now, the true reason why I became interested in that question is because before I learned anything about this geometrical characterization, neural collapse, and ETF, I had been interested in this question of understanding why large models struggle with imbalances and how we can design better loss functions for it. And as a matter of fact, we had a work just prior to this neural collapse with my students and Summit, who I think you are all familiar with and will join you very soon. And so in our original work, we were trying to address these questions by looking at linearized models, because at the time this is what we could get a handle on. And I kind of saw this type of structural characterization as a different approach that potentially could help us extend this theory to nonlinear models, and this is something that I want to discuss. And as a final remark here, I will say that looking at imbalances, I think provides a pathway towards trying to understand whether there is and what is the link between generalization and this type of geometry. So what I want to do in this talk is I want to mostly talk about this part 1, which is answering the question of whether it's possible to find structural properties when data symmetry breaks. And then in part 2, I want to start discussing, and I can talk more offline regarding this if people are interested, about understanding, using this type of knowledge to try to understand why models struggle with imbalances and how we can design better losses using this geometry information. Okay, so this is going to be the first part of the talk, which is together with my students Ganesh, Val, and Tina, and this is work that has appeared recently. So let me pause here maybe and see if there is any questions. Otherwise, I will continue with part 1. Okay. Good. So let me continue again. Please feel free to interrupt. So here is the setting that I will be discussing. It's a class imbalance setting, as I mentioned. So we have now k classes, but a fraction row of them are minorities. And these minority classes, they have a number of examples that is r times less than the number of examples in the majority classes. So the only 2 variables that I want you to remember from here is k, which is the number of classes, and r, which throughout the talk is going to denote this imbalance ratio. So if r is equal to r, then I'm back to the balanced case that was discussed previously, but I'm interested in scenarios where r is larger than 1. So the larger the r, the higher the larger the imbalance. And so here's our result in a nutshell. the postulation is that the geometry in this step imbalance setting is characterized by the following two properties. So the neural collapse property remains unchanged, but the ETF property changes to something that is more general, and we call this the simplex encoded labels interpolation, or SELI property in short. And so what I will do is I will explain to you what this SELI property is and try to give a sense of how we came up with it. Before I do that, let me just show you a picture. So this is how the geometry would look like. The SELI geometry would look like in a scenario where I have four classes, a minority ratio of rho equals 1/2. So this means that we have two majorities and two minorities, and imbalance ratio R equal 10. Okay. So the first thing to observe here is that the geometry compared to this ETF, very symmetric ETF structure that I showed you previously, is now asymmetric. So you see, for instance, that the angle between the minority classifiers, which is these red stars, is smaller than the angle between the majority classifiers. That's probably something not very easy to see. What is easier to see is, for instance, that the norm of the classifiers of the majorities is larger than the norm of the classifiers of the minorities. Okay, and so as a matter of fact, let's do the following experiment. So we're going to train CIFAR10 and MNIST. We're going to train an imbalanced version of these, and we're going to look at the ratio of the norms of the majorities, of the classifier majorities, to the classifier minorities. And we're going to compare this to a theoretical value. And I'm going to compare this to the theory value predicted by the ETF geometry. And I'm going to be plotting these things in dashed lines. And I'm going to compare it also to the theoretical value predicted by the SELI geometry. And I'm going to see how this measure evolves as a function of training. Okay, so as a function of epochs. And the point that I want to make here is that for different values of R, which is the imbalance ratio, the new theory value, which is the SELI value, predicts what this ratio is, while the ETF value, which is just 1, would be divergent. Okay, so you see that the solid lines here, which again are comparing this empirical value to the SELI value, are driving to 0, while this is not the case for ETF. So at least empirically, it appears that this SELI formulation captures at least the ratio of the norms of the classifiers. Now, this is not specific to the norms. You can do the same experiment for the gram matrices. And again, the gram matrices, the diagonals would capture the norms, and the off diagonals are going to capture the angles. And you can try compare this to the corresponding theoretical value of the SELI or the ETF geometry. SELI is in solid lines, ETF is in dashed lines, and you see these experiments run for different values of R, and you see that consistently this new value for the gram matrix predicts better what is happening in practice. Now, this is also the case for the embeddings. I'm going to mention, though, that again we see something similar to what we observed even in the balanced case, that the convergence the convergence floor for the embeddings is higher than the convergence floor for the classifiers. And also note that as the imbalance ratio increases, convergence does slow down. So this is something that we see consistently in our experiment. Nevertheless, convergence is still better for this SELI geometry compared to ETF. Okay, so I think it's time that I tell you what the SELI geometry is, because until now it has been some mysterious theory. Okay, so the SELI geometry really comes from, and this is why we call it SELI, it comes from a simplex encoded label matrix. So what is that? This is a K times N matrix. It's an encoding matrix, so it has as many rows as the number of classes and as many columns as the number of examples in the training data set. So in this running example that I've been going through, where you have 4 classes, there's 4 rows, and maybe the first 50 columns correspond to the first majority class, and then the second 50 columns correspond to the second majority class, and then the last 10 columns are for the 2 minorities. And the entries of this matrix are exactly, can take 2 values. either k minus 1 over k or minus 1 over k. Okay, so this is a matrix where every entry can take either one of these two values. And essentially what this matrix is the vanilla one-hot encoding matrix, which is just a 0-1 matrix when you center it by subtracting 1 over k 1 transpose. Okay, so this is what we call the simplex encoded label matrix. So it's an encoding matrix that is slightly different than the one-hot encoding matrix. And why it is a central object in this study is because the geometry is given in terms of the SVD of this matrix. So if you write V lambda U transpose as the SVD of this matrix, which you can show very easily that it's of rank k minus 1, then what describes the SELI geometry are these two properties. So the gram matrix of the embeddings converges to V lambda V transpose, and the gram matrix of the the gram matrix of the classifiers converges to V lambda V transpose, and the gram matrix of the embeddings converges to U lambda U transpose. Okay, so this is what we postulate as the SELI geometry. So the picture that I showed you previously is nothing but me writing down the cell matrix for the corresponding case of k classes. Note here that the way that the imbalance ratio is encoded in this matrix is implicit, and the encoding is being done with respect to how many columns correspond to its class. Okay, so in a balanced case, I would have the same number of columns for its class. Here you see that I have more columns for a corresponding class. So this is what changes the left and right singular vectors and the singular values, and this is what changes the geometry. All right. In fact, what is interesting, I think, here is that we can actually compute these SVD factors of the cell matrix in closed form. And what this means is that it gives explicit expressions for the norms and the angles in terms of the parameters, the only parameters that play a role here, which is the number of classes, the imbalance ratio, and the fraction of minorities. And so let me give you an example. Again, the very details don't matter here. What I want to say is that it is possible to write down what is the ratio of the norm of the majorities to the norm of the minorities as a function of R and K. Okay, and it's some formula, but it's a closed form formula. And in the experiments that I showed you previously, where I claimed I have some theory value that I'm comparing against, this was the value that I was comparing against. Okay, so what I'm claiming here is that we can predict what is this ratio at the end of training. All right. Now this is not specific to the norms of the majorities.
Hi, Christos, I have a question. So
yes,
here you are measuring the norm of like a classifier and the features. So what if you normalize the norm of the feature and the classifier? You can do it like in your network, just doing a normalization after like you train the features. So does the geometry changes, or I think essentially the angle would be matter when you do the classification path, right? So yeah, I wonder whether if you normalize the features, what will happen.
If you normalize the features, well, if I normalize the classifiers, obviously this ratio would be 1. So here I'm not doing any normalization, I just let it run.
Yeah. So you are using the cross-entropy with like
I'm just using all this is with cross-entropy. This is just with cross-entropy
with like a regularization. Is it any regularization or will?
Good question. This is with the standard very small regularization. So 10 to the minus 4.
I see.
So very small weight decay. Not regularization, weight decay. Yes. So there is no normalization, explicit normalization. That's not. Now the norm will matter, of course, and the angles also in the as you say in the margins, right? And that's something that we will try to take care in the second part of the talk.
Okay.
So this is all with percent. Yes.
One more question I would like to ask. I could see that as the imbalance ratio increases R, your SELI approach to that ETF. What's the reason for that?
Why are you saying that? That's not. I
yeah,
don't think that.
In this figure, if you can see that as the value of R increases R1, 5, 10, 100, and then it approaches to ETF goes something like that.
Well, okay, so maybe let me make clear how to read this figure. So the dashed line shows how much the geometry approaches ETF. So as R increases, it actually goes further away from ETF, because you see that the distance to ETF, if I call this metrical distance, goes to the value 4, while for the distance to SELI, it goes to 0. So I wouldn't say that it goes closer to ETF. I don't know if this was clear.
No, can you just go one slide back where you were showing the ETF and
embeddings?
Just one more slide. Here.
Okay.
Okay, it's clear. Thank you.
Yeah, so it's the dashed line goes up. It is true that the solid line goes to 0 slower, so you're definitely right, as imbalance ratio increases, but still the gap to ETF is large. At least for the norms, we get very good convergence, which is not necessarily the case for when you account for the angles as well. So I'll show more of these plots later. I think it will also become more clear.
Okay, thank you.
All right. So as I mentioned, it is possible to find closed form expressions, so how these angles and norms change as a function of the imbalance ratio, and you can plot these closed form functions. Okay, you can plot this as a function of the imbalance ratio, and again, many plots here. Don't worry about them. Let's just focus on one of them. Let's focus on this plot in the center, which measures the cosine of 2 minority classifiers as a function of the imbalance ratio. Okay, and so this shows that for 3 different values of k, so blue is 20, green is 10, and red is 4, it shows how this cosine evolves as a function of the imbalance ratio. And so one thing to observe here is that as r goes to infinity, so in the large imbalance ratio limit, this cosine becomes 1. And so this is something that was actually discovered by a group of people from UPenn just after the original discovery of neural collapse, and they called this minority collapse. So they looked at the imbalance and the imbalance case, and they only looked at this limit of very, very large imbalance ratio, and they postulated that there's a minority collapse that is happening. So what I want to show here is that this follows as a special case of this result, and it actually shows several features of the result. One thing that it shows, for example, is that as long as the regularization of the weight decay is very small, which is our setting, then this minority collapse really happens only where R is very, very large. And also they have several experiments in their paper where, for example, they kind of measure how fast this neural collapse happens as a function of k, which is the number of classes. So this is something, these are type of results that you can get a better understanding through the more refined characterization that we have. And if people are interested, there's an entire section in the paper discussing these comparisons. But beyond that, again, this type of SELI geometry has expressions that are valid for every value of R, so it's not only an asymptotic result, and in principle, it holds both for classifiers and embeddings and norms at angles. Okay, now the question is how to come up with this, right? And I think to me the most surprising feature of the original paper by Papsian, Han, and Donoho is how did they come up with this geometry? Because once you have the geometry, it takes a lot of work, but it's rather a standard pathway to cast metrics that measure the distance to this geometry and try to see if this geometry is really happening. Of course, it takes a lot of effort to do these experiments, but really the key question is how do you know this geometry is true? And so the way that we do that is by relying on this very nice idea of an unconstrained features model. So this is something that sort of showed up in a series of works that followed after the original paper that were that postulated that used this type of unconstrained features model in order to explain the ETF geometry and the neural collapse. And so this unconstrained features model is saying that we can essentially treat all layers, but the last one as a powerful black box that can generate unconstrained features. And this is aligned to what I told you in the beginning, that in this talk, we're going to be just focusing on the last layers of the neural network and seeing the rest as a black box. This says that you should look at this black box as a very powerful black box that can generate any type of features you want. And so now when you look at your training objective, it looks like what I showed you previously, only now the minimization is not only not only over W, but is also explicitly over the feature vectors H. So previously what I was doing is I was minimizing over these parameters theta that were parameterizing the embeddings with respect to the architecture of the neural network. Now I am explicitly minimizing over the embeddings. So this is still a non-convex optimization, but it's a simpler one because H is unconstrained. And this is the unconstrained features model. And it's something that, as I mentioned, has been used in a series of works in order to explain the ETF property. And I've highlighted here one work. So this is work by Tsing's group. And I'm not highlighting it here just because I'm giving the talk to this audience, but it's actually the paper that I learned this analysis from, and I think it's very well written. So the result in their paper is actually they show that the global minimizer of this objective, of this unconstrained feature model, is the ETF geometry. Okay, and if my understanding is correct, essentially the way that they do it is by sequentially applying Cauchy, Schwarz, and Jensen lower bounds to these cross-entropy laws, and you can do that because things are balanced, and then tracking the inequalities, you try to make all these inequalities equal equalities, and you notice that equalities are satisfied if and only if the neural collapse and ETF property holds. Now there's a deeper result to that, which is showing that the optimization landscape is actually benign. So in fact, in this paper, they actually show that any critical point is either a global optimizer or a strict shuttle, which essentially means that gradient descent will get you to this global minimizer that has the desirable properties. But in our case, we're in a situation where there is no symmetry, and we actually don't know what to prove, right? So at least myself, I don't know of a way of sequentially applying some type of Jensen or Cauchy-Schwarz type inequalities that would give me a lower bound and then try to make this lower bound tight. So we follow a slightly different approach, which is as follows. So it's sort of a three-step approach. The first step is this observation that what changes in the imbalance setting is that the value of the regularization now matters. In the balance setting, whatever value of lambda you have here, the solution is the same, meaning that the global solution always has this neural collapse in TTF structure. Once you go in the imbalanced case, this is not the situation anymore. And so what we suggest is look at the limit of lambda going to 0, and look at this limit because this is what aligns with the current deep learning practice of using weight decay that is very, very small. Okay, so no explicit regularization. So take the limit of lambda going to 0. Now, when you take the limit of lambda going to 0 of this objective, then you can show that the solutions will converge in direction to the solution of a max margin problem. So this is a hard margin. You can view this as a hard margin SVM problem. In fact, if you ignore the Frobenius norm of the features on the objective function, this is exactly the multiclass SVM problem. So this is a version of a non-convex multiclass SVM, where you're minimizing the Frobenius norm of both the classifiers and the embeddings, subject to separability constraints. And so the main result is showing that the solution, the global solution to this non-convex max margin problem is given by the SELI geometry. And so what this means is that if W hat, H hat are global optima of this SVM, then they have to be such that their gram matrices are given with respect to the SVD of the cell matrix that I described previously. Okay. Now, how do you show that? The proof is not very surprising. It follows standard proof technique in these situations of non-convex problem. So we formulate a convex relaxation, and we use a dual set. We construct an explicit dual certificate to show that Z hat is the unique solution. A bit more specifically, this is the convex relaxation that we're using. Again, we are not coming up with this. This is something that that was known and has been used in previous neural collapse papers. Starting from this relaxation, we look at the dual. The dual looks ugly, and the reason is that there is k-1 constraints for each example, so it's a little bit asymmetric. And so really the key observation here is that you can rewrite the dual in a form that explicitly is explicitly parameterized by this cell matrix Z hat. That is the quantity that I want my result to depend on at the end of the day. And so when you rewrite the dual in this form, then the result is much more clear. So you can already see here that this is an SDP. Okay, it's an SDP because I have a spectral constraint. And so the first two constraints are actually very simple. What makes this SDP difficult is the last constraint, because the last constraint is a constraint that requires a specific sign patterns for this dual variable B. Okay. So the way that we go about showing that what is the solution to this is by removing this constraint, solving the unconstrained problem, which is very easy to do, and then showing that the unconstrained solution satisfies this pattern. So this is really the challenge in the proof. And then the path is straightforward. You use KKTs to show that B hat is the unique dual optimal that produces Z hat as the unique primal optimal. Okay. Now, I want to say very quickly that this result just characterizes the global optimum. There is still the question of whether gradient descent converges to this global optimum. This is something that you could try to approach by looking at this unconstrained feature model as a two-layer neural network, with the first layer being the embeddings, the second layer being the classifiers, and the inputs being the basis vectors. Again, this might not be obvious at the first sight, but it's something that is easy to see, that this unconstrained feature model is
Chris, I have a question.
Yes.
So for the geometry, the SELI geometry, you don't need the class number like larger than the feature dimension. I think
I do need that.
I mean,
I do need
I just want to know whether this proof or depending, the D
do
larger
need,
than.
Yes, I do need.
So for this global optimality analysis, do you need D larger than K, or this is? I mean, for the geometry holding, you need that, right? For the global analysis, I'm not sure whether this is needed, and this could be,
Yeah, I don't know the answer to that thing.
Okay.
Actually, yeah, we haven't done the convergence analysis.
Just for the global optimality. So I think for self-super learning or other scenarios, there might be a case where D is smaller than K, and that could be some interest.
Yeah, absolutely. That's definitely interesting, and I don't know the answer to that.
Okay.
Yes. Yes, and so in fact, I don't know whether gradient descent. I don't know how to prove that gradient descent converges to this global optima, or that this global optima is benign, in this case where lambda is 0. By using this type of implicit bias results, essentially the question, one way to view this question is whether the stationary points of this global optimization, whether this global optimization point is one of the stationary points that gradient descent converges to. And this is something that is known for the binary case. It has been recently shown for the multi-class balanced case. I don't know for formal proof for the imbalanced case. This is something that we see happening in experiments. Convergence is slow, as it is for the balanced case, but it's actually even slower as imbalance ratio increases. So I think, yes, I think there is interest here. One potential way of showing that is by connecting the gradient descent path to the regularization path, which we have some preliminary results on in the paper, but I don't know if a result that formally shows this connection in the non-linear multi-class setting? So I think that's an open question that is interesting, at least from our lens. Okay, so I think I'm going to summarize this first part. So we saw that the solution of max margin follows the SELI geometry, and I showed you evidence that this is something that happens in deep nets. So experiments support this hypothesis, but convergence is slower for embeddings, and thus imbalance ratio increases. And what I want to do next is I want to talk about a little bit about how we can use this understanding to design better algorithms for imbalanced data. Seeing how much time do I have?
I think it's until 10:30. Yeah, and plus all the questions.
Okay. So I have okay. Good.
Take your time.
I'll start and you can. Yes. Okay. Good.
Okay.
So this is work that is a bit more recent. It's going to appear at AIA Stats, and we put the paper in archive. So what do we want to do here? We want to change the cross-entropy loss to do better when we have imbalances. And by do better, I mean do better in terms of test error. Okay. And now, why do I want to change the cross-entropy loss? Because if you train an imbalanced data set with cross-entropy loss, not surprisingly, what will happen is that the minority test error is going to increase, and this is going to translate to a rather significant increase to the balanced error, which is the standard metric that you should be using if you're looking at imbalanced data. And so you see that I have a standard error of 16% for the balanced case that jumps to 35% when the imbalance ratio is equal to 10. And so, of course, the fact that cross-entropy loss is bad for imbalanced data is something that everyone knows. And the standard cure in machine learning, or one standard cure, has been to use weighted cross-entropy. Okay, so instead of minimizing the cross-entropy loss, use a different loss, which is the weighted cross-entropy, where you now upweight the contribution of minorities to the loss and downweight the contribution of majorities. Now, what makes interesting the study of imbalances in large models, in overparameterized models, is the fact that this weighted cross-entropy loss actually fails if you train in this regime. So if you train and you continue training beyond the 100% training accuracy, so if you don't early stop, then a series of works have shown, mostly empirically, but also with some theoretical arguments, that weighted cross-entropy fails in this regime. And so really the question that we want to ask is whether we can design a different loss function that does better. And we're going to ask this question from the viewpoint of the implicit geometry. Okay, so what we know from the first part of the talk is that if we train with cross-entropy loss, then we have a geometry that is asymmetric. So I have possibly, I talked about minority collapse. So I have, for example, an angle between classifiers of minorities that is smaller. And so is there a way to come up with a different loss function such that when I train, the geometry remains symmetric even when I have imbalances? Okay, so can I design a loss function with an implicit geometry that is symmetric and avoids minority collapse and has a better alignment between embeddings and classifiers? So the answer to this is yes. You can do that by using this vector scaling loss. So this is a loss function that is again a parameterization of the cross-entropy loss, but is different than weighted cross-entropy. The way that you parameterize the cross-entropy now is not by multiplying the logarithms in the front, but what you're doing is you are scaling the logits. And you are scaling the logits with this hyperparameters delta that you have a different value of delta for different classes. And the main result of the paper is a characterization of the implicit geometry of this vector scaling loss. And so in fact, what we do is we're going to look at two special cases, just for the sake of transparency of the results. We're going to look at two special cases of the VS loss. The first one we call the CDT loss, and the other one the LDT loss. The CDT loss, what it does is it gives a different hyperparameter to its classifier, and the LDT loss gives a different hyperparameter to its embedding. Okay, so you can view them as two different types of cross-entropy parameterizations, both of them with respect to these hyperparameter deltas. And so what we saw is that there is a geometry, which is some variation of the original SELI geometry that describes how the embeddings and the classifiers of the CDT and LDT laws look like. Okay. Now, I'm not going to go into explicitly defining this geometry. This is defined with respect to some different encoding matrix. Now, what is important, what I want you to keep in mind here is that this new geometry is going to be parameterized now, not only by the number of classes and the imbalance ratio, but also by the hyperparameters that I'm using. And since I am in this step imbalance setting, where I only have one level of majorities and one level of minorities, I'm going to be using the same hyperparameter delta majority for the majorities and the same hyperparameter delta minority for minorities. And I'm going to call the ratio of them capital delta. And you can show that the geometry only depends on this capital delta. Okay, so this is really what captures the hyperparameters. So I'm not going to show you an explicit formulation of that, but this is how different aspects, different features of the geometry look like. So what I'm doing here is I'm parameterizing, I'm fixing R, okay? So I'm fixing the imbalance ratio, and I'm parameterizing this hyperparameter delta as R to the gamma, and I'm swiping gamma, I'm changing gamma, and I'm showing you how the geometry changes, okay? In particular, I'm showing you how the norm ratios change, how the angles change as I swipe gamma. Gamma equals 0 corresponds to the to cross-entropy laws, and this would be exactly the values of the SELI geometry. Now, this is just a postulation, right? So this is theoretical curves. Again, there's no really theory here, but it's just a formalization, and these are the corresponding curves of the geometry. Is this something that predicts what is happening in practice? Well, here are the results. So what you see here is you see empirical data points of the corresponding quantities measured for 3 settings where we train the unconstrained feature model, we train an MLP, and we train a ResNet. When Vala first suggested to me of doing this experiment, I was rather unconvinced that we could get any sort of good agreement. I was rather struck myself personally to see, for example, that we get such good agreement for things like the norm ratios or the angles between majorities and minorities. There is certainly deviation, right? So there is some quantities that you see a disagreement, but I would say that overall, I think the agreement is pretty satisfactory. Okay, again, this is what we're doing is we're training, say, ResNet 18 or on CIFAR 10 with imbalance ratio 10. We're using a differently parameterized loss function, and as we're swiping this hyperparameter, we're trying to predict what is, say, the ratio between majorities and minority norms. Okay, and we get a pretty good prediction for what this is. The same is true for LDT. I'm not going to go into details on that. Now, really, the question is that I started with is can we tune the CDT and LDT laws to create a geometry that is more symmetric? So can we tune it in a way that we get alignment and we avoid minority collapse? And so it turns out that there's a special tuning that can achieve that, and this tuning is the same for both LDT and CDT. So if you choose this hyperparameter delta to be equal to square root of R, so if you choose this gamma to be equal to 1/2, then the LDT geometry becomes actually the same as the ETF geometry up to a scaling of the majority embeddings. So you see here that I have the equiangular property, but I only don't have the same scaling of the embeddings of the minorities to the majorities. The CDT geometry achieves alignment. It does not achieve equiangular property, but actually the angle between the minority classes is now larger than the angle between minorities and majorities. So maybe that's a favorable feature. And in fact, we have an argument that CDT is more robust to LDT. And one nice way to see that is by looking at the large imbalance ratio limit. So if you look at what happens when R goes to infinity and you have parameterized these deltas R to the gamma, then for LDT, when gamma is equal to 1/2, you get coangular property. Okay, so this is what I started with, my desirable thing. Okay, but then if I deviate from this gamma equals 1/2, then I get either minority collapse or majority collapse. So there's just one special value of gamma that achieves this good behavior. For CDT, I can never achieve equal value between minorities and majorities, but there is an entire range of gammas. So as long as gamma is larger than 1/6, then there is a clear separation between minorities and between majorities. Okay, and so in that sense, we say that CDT appears to be more robust. Okay, now the elephant in the room, and I'm going to close with that, is generalization. How does this geometry, if it does, how does it translate to test error? Why this question is not obvious? Because this geometry is something that characterizes behavior at training time. And so perhaps a simple model to try to see what happens at test time is to imagine that what happens at test time is that around the training geometry, the test examples will be Gaussians around the corresponding mean vector. Okay, again, just a very simplified, first very simplified model. And so here's what you see, that we're postulating, and this is something that we actually observe, that at test time you don't get the embeddings to collapse as well as at training time, so they are dispersed around the corresponding mean vector. And in fact, we're gonna assume in this model that the variance is larger for minorities. Okay, again, perhaps the intuition for that is that you've only seen fewer examples, so you have a less accurate sense of what is the mean for this class. And we're gonna
Christos, so for testing, do you also assume the testing data are imbalanced or they're balanced, or?
Good question. So I'm gonna assume that they are balanced.
Oh, okay.
Yes, I'm gonna assume they're balanced because what I want to measure is I want to measure the balanced error.
Got it.
But nevertheless, I'm going to assume that the way that they're dispersed around the training mean, it has a larger variance than the majorities, and this variance scales as r to the alpha for some value of alpha. And in order for me to be able to compare different geometries, I need to normalize things somehow, because as geometries change, the norms change. And so we're going to assume that the total geometry, we're going to fix the total SNR of this geometry. Okay. And so now you can evaluate this balanced error, at least in theory, for any given geometry. We can use Monte Carlo to evaluate these Gaussian integrals, and this is how figures look, how the balanced error behaves as a function of this hyperparameter gamma for CDT and LDT loss for one value of alpha. Again, this is not binding. As I change the value of alpha, this picture will change. So I just want to get qualitative conclusions from here. So here, one thing to observe is that, okay, it looks like the range of gammas between 0 and 1 is where maybe I should expect my balanced error to be small, and around 0.5 is where I should expect the geometry to have a good balanced error. Okay, so this is, again, just a very simple and naive model. Let's see what happens in practice. So here are the experiments. On CIFAR-10, MNIST, and Fashion MNIST. I'm showing you balanced accuracy, majority accuracy, minority accuracy, too many plots. So let me just focus on balanced accuracy, where we're comparing 3 losses for changing values of hyperparameters. We're comparing the CDT loss, the LDT loss in green, and the weighted cross-entropy in blue, in red. Okay. So the first observation is that both CDT and LDT improve on cross-entropy and weighted cross-entropy. Cross-entropy here is shown for the value of gamma equals 0. You see that all the curves overlap. And the reason is that for gamma equals 0, they're essentially all the cross-entropy loss. So you see an improvement for both CDT and LDT. The improvement that we get for CDT is significant, is more significant than the improvement that we get for LDT compared to cross-entropy and compared to weighted cross-entropy. It appears that gamma equals 0.5 is a consistently good choice, okay, for all the data set. Nevertheless, it's not the optimal choice, okay? So that's perhaps something that we should expect, that maybe this gamma equals 0.5 gives a rough guideline, but then you can certainly fine-tune things for the specific data set. So the optimal value for this data set is different than 0.5. Now, the next observation is that LDT is sort of not living up to its expectations. Okay, so according to the theory generalization plot that I showed you previously, I would expect LDT to behave quite similarly as CDT. Nevertheless, you see that it does not achieve as high test error. Here are two possible explanations for that. The first explanation might be that, as I argued, CDT is more robust than LDT, and maybe that translates to practice. Or actually, it might be the case, and that's something that we've observed, is that the type of deviation is more intricate than what I assumed before. Nevertheless, we can still use this implicit geometry to improve the LDT performance by doing a post-hoc rescaling scheme. And this is something that I don't want to go into detail. I can talk about it offline, but what you can do is you can essentially take your classifiers and rescale them after training, and then you can get a boost in performance and you can achieve the same performance as CDT. But you need this extra step. That is of no cost in training, but it's still an additional step. So I think I've gone over time. So I will summarize quickly by mentioning a few limitations of the work and an outlook. Okay, so I want to say that this geometry characterization has this feature of being asymptotic in the number of training epochs. So we see this phenomena only when we train for large number of epochs. The convergence varies between architectures, datasets, imbalance profile, and loss that is being optimized. Yes, there is a universality feature, so there is a cross-situation feature on the trend of these curves, but the actual convergence speed and convergence floor varies as we vary these features of the study. There's still no explicit link between geometry and generalization. I showed you some what I think are preliminary investigations, and others have such investigations as well in this direction. And I want to close with an outlook. This quest for implicit geometries and characterizing the exact geometry of embeddings and classifier, I think we'll all agree that is non-trivial. We're looking at these complex architectures and data sets, and we're trying to understand how they behave under different distributions and different losses. And so that said, I think that the level of agreement that we see is rather striking. And it's also encouraging the fact that we can use this type of geometry characterization, this implicit geometry, to guide the loss design. So I think I will stop here, and if there's questions in the remaining time, I'm happy to try to respond. Thanks again for your attention.
Thanks, Christos, for the great talk. I actually learned a lot from your talk. Any questions for the speaker?
Yeah, I have a quick question. Thanks for the great talk. So I was just curious, when folks use data augmentation for their data sets, like how does that affect the geometry? Is that somewhere between like a SELI geometry and a ETF? Yeah,
that's a very good question. Okay, so let me just clarify at least what our results correspond to. So this type of results that I showed you, which show convergence, are without data augmentation. Okay. In the experiments for generalization, we do with and without data augmentation. And of course, data augmentation improves performance. So this is shown here. So these experiments are with data augmentation, but this is something that you see here. So with data augmentation, the balanced accuracy goes up. Qualitatively, the nice thing is that we see the same boost of performance that we expect, irrespective of whether we're doing data augmentation or not. But my short answer to your question is that all our convergence investigations have been without data augmentation. With data augmentation, the convergence is not that good, but I think it depends on the data set. I don't want to say that it's in general worse, but maybe let me just say that we haven't investigated as far as the non-data augmentation in terms of convergence to the geometry.
Thank you.
But that's a great question. I definitely don't know how to capture that in the unconstrained features model.
Yeah, I have a question for the loss design. So the previous work, there's some other work on the imbalanced case where they fix the last layer, like a classifier's ETF. So I wonder how, I mean, look at your loss. It seems like you just adjusting the classifiers, and also there's a way to adjust the features. I wonder how does that compare to just to fix the WS ETF, and also normalize your features or something. Yeah, just
Yeah, no, this is right. This is a good question. So I guess there's two aspects to this question: is how do the results change in terms of the geometry, and how do they change in terms of test error?
right.
So the purpose of this work was not to design a state-of-the-art loss. Okay, so definitely, if you do post hoc on top of that, it will help. If you do some rescaling. So we have not explicitly compared to say doing normalizing the features or fixing the W's to BTF. Again, because at least my the way that I arrived at this is understanding how changing the loss itself would
Yeah, but I think this is more systematic.
Yeah, it's but that, I think that's kind of a debate on whether you should be doing something like that, or whether you should train with cross-entropy, trust your features, and then just do a post-hoc rescaling at the end. So there's more and more works that say that maybe this is what you should be doing, especially if you're training a very large model on big data sets. Maybe despite imbalances, your features are still robust. But I don't yet know how to. Well, I would be interested in trying to understand this from this viewpoint of implicit geometry, but I don't yet know the answer to that.
Yeah, thanks.
That's interesting.
Yeah, can you remind me how the deltas are chosen?
Yes, so the deltas are hyperparameters. Okay, so in practice, the most general version of the vector scaling loss is like that, right? So you could, in fact, this is what we had in the original paper with Ganesh and Orestes, my students, and Summit. We had this loss, and the way that we're tuning is by doing a grid and tuning them. And I was hoping that by using this implicit geometry, we would get a better understanding of a better guidance for tuning them. And so the way that we're tuning here is by parameterizing these deltas. So first of all, since we're discussing step imbalance settings where I have minorities and majorities, I'm fixing the deltas of all majorities is going to be the same as the deltas of all minorities. And so the only thing that matters is their ratio. And so what we're doing here is we're parameterizing this ratio capital delta as R to the gamma. Now, why you're doing that? One way to think of why this might be reasonable is if you think what you are doing in the weighted cross-entropy case, the standard way to tune weighted cross-entropy is to take these weights and make them be inversely proportional to the probability of the corresponding class. So think of what we're doing as doing the same parameterization, but raising this to a power of gamma so that we have some flexibility. Now, in terms of the implicit geometry, the reason that you would do this R to the gamma is because of this, that if you do R to the 1/2, then you accomplish this symmetric geometry. So this is the specific type of tuning that we are looking at. Maybe one thing to add to this is that although what matters is only the ratio, this delta, that's not entirely true, because you're going to have optimization issues that are hidden under the rug here. And so the specific setting, what we do here is that we fix the delta minority, we fix the L1 norm of these deltas to be equal to 1, and then we scale appropriately, right? So we no matter how R and gamma changes, we fix the L1 norm of these deltas to be the same. And again, this is because of optimization issues. Otherwise, we can't drive the loss to zero.
Great. So due to the time limitation, let's thank the speaker again. And for those you guys meeting up with Christos, yeah, you can bring up more questions with him.
Thanks a lot.
Yeah, thanks. Talk to you later.
I'll
Do lunch.
Yes. Thank you, guys.
Bye.